Hello, ladies and gentlemen. I think you're going to enjoy this. I'm going to start giving you tests. Remember, back in 8.2, we started dealing with what I referred to as cornerstones, or sort of home bases. And that was remember we had the harmonic series, which we know diverges. That was this guy, the harmonic. As n goes from, who cares, as long as it's not zero, right? 1 over n. This guy diverges, right? We had this guy. This is the geometric series. 1 to infinity r times a to the n minus, a times r to the n minus 1. Or we could start it at 0. Remember that one? Theoretically, we can start wherever we want, as long as we're dealing with positive integers. We just have to rename what we're dealing with. But I don't want to get too crazy with that. I can either write this like this, or I can write it like n equals 0 to infinity of a times r. And we know this guy converges if absolute r is less than 1, and we know that it converges to the sum, which is equal to a, whoops, just lost my dingle there, a over 1 minus r. Okay, so those are home bases. But what we need to be able to do, we need to start talking about things, we need to start talking about tests. We need some actual tests that we can apply to these series. Because I'm going to throw series at you and you're going to be like, oh my God, if it doesn't look exactly like that or exactly like one of these guys, you're not going to know what to do. Remember the telescoping series? That was another example of that. So let's take the series just for giggles. Let's do, I don't know, let's do 1 over root n. Okay, and we'll go from n equals 1 to infinity. And I'm going to see if this thing converges or diverges. Now, the easiest way to do this, and it's actually quite cool, is I'm going to think of this as though it comes from the function f of x equals 1 over root x. Well, think about what 1 over root x looks like. It looks like this, right? Remember this guy from improper integrals? If I take that, if I take this thing all the way out to infinity, then that's what it's going to look like. Now, if I start at 1, now my scale is going to be a little jacked here, so just bear with me. So let's go 1, 2, 3, 4, 5. Okay? If I start at 1, now notice that these rectangles are 1 wide, right? And this is going to be f of 1 tall. So if I build this rectangle right here, do you agree that this is going to be a sub 1? If I build this rectangle right here, this is going to be a sub 2. If I build this rectangle right here, a sub 3, etc., etc. So this sum, right, I know if I take n equals 1 to infinity of 1 over root n is really going to be, for this guy, a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n plus dot dot dot. So it goes on forever. Do you agree, just by looking at the way in which I built this, do you agree that this is definitely going to be greater than the integral from 1 to infinity of 1 over root x dx? Right? Remember that? We saw this. This right here is an improper integral. And we proved it. We proved that this guy diverges. Remember, it was called a p integral. Remember that guy? Well, just think about from improper integrals. Let's have a quick little review. If I take the integral from 1 to infinity of 1 over x to the p dx, 1, if p was greater than 1, then this converged. 2, if p was less than or equal to 1, then it diverged. Right? And this is, of course, for p's greater than 0, otherwise it flips up. That's an x to the p. That's badly drawn. So think about what happens here. If I have a sum of terms that's going to be greater than something that diverges, then what does that imply about the series itself? 1 over root n must do what? Well, again, this is just the geometric representation of that series. So guess what? It diverges. Now, let's look at another one. Let me give you, how about this guy? How about the sum as n goes from 1 to infinity of 1 over x squared? And let's analyze it in exactly the same way with one little twist. I think you'll like this. 1 over x squared goes just like this. But we know, if we think about, in the back of your head, If I look at f of x equals 1 over x squared, if we've got in the back of our head, we remember that the integral from 1 to infinity of 1 over x squared dx, this thing converges because of our rules about p integrals, right? If p is greater than 1, which 2 is clearly greater than 1, then we converge, and we proved that way back in the day. Now, I'm going to do something a little bit funky here, but I think you'll think it's pretty cool. Watch. Now, using exactly the same idea that I did over here, I'm going to put a 1 here, I'm going to put a 2 here, I'm going to put a 3 here, you get the picture, and I'm going to put a 4 here. Now watch, there's a problem, okay? That what I end up with is a bunch of rectangles that are greater than something that converges. And you remember back when we dealt with improper integrals, if we were greater than something that converged or less than something that diverged, we were like, nah, I can't really tell. But watch this. Remember, all that I need to make sure is that each one of these rectangles is 1 wide and then f of n tall, right? So why can't I build this rectangle? I'm going to build that guy right here and call that A1. It's 1 wide and f of 1 tall. I'm going to call this A2. It's 1 wide and f of 2 tall. You see how I'm breaking no rules. Now I know your spidey sense is tingling, and rightfully so, but give me just a sec. Now think about that for a sec. Why couldn't I do exactly the same thing over here? Why couldn't I build this guy and this guy and this guy and this guy? Well, I could, but then I would be less than something that diverged, and I can't draw any conclusions from that. It was the same thing as with the integrals, right? However, I know for sure that I can build something that is greater than something that diverges that represents the series. I can also build something that's less than something that diverges, but that doesn't give us any information. So as long as I can build something that I know is either greater than something that diverges or less than something that converges, then I know for sure that I can build something that either converges or diverges. In this case, I built something that diverged. In this case, I built something that converges. All right, this is x squared, and I know that this converges. All right, now there's something super powerful about this right here. It's amazing. It's called the integral test. All right, and the integral test, let's just write this thing up. It's your first real test other than one of your home bases. It's called the integral test. Okay, and all that it says is, it says suppose that f of x is a positive, so it lives above the x-axis, decreasing function. Whoops, not function. I don't even know what a function is. Sounds gross. Function, sorry guys, on the interval from 1 to infinity, and a sub n equals f of n. So there's our supposition. All right. If this is how I started off, then this implies that if the integral from 1 to infinity of f of x dx converges, then this implies that the sum, as n goes from 1 to infinity, of a sub n converges. If the integral from 1 to infinity of f of x dx diverges, then this implies that the sum, as n goes from 1 to infinity, of a sub n diverges. Now, that may seem really, really contrived to you. It's like, whoa, first and foremost, I got to have this function that's positive, that's decreasing on this function. However, it becomes real, and wait, let me back up. You would be correct. That is very contrived. However, the ramification of this test gives us something wonderful, and it's called the p-series. The p-series falls out directly. Think about this. Remember this rule over here about, about improper integrals? Well, you combine this rule about improper integrals and this integral test, which we sort of loosely geometrically proved here. Isn't it true that if I have the sum as n goes from 1 to infinity of 1 over n to the p, this is like I had a p integral here, now this is a p series. Remember, 1 over n to the p comes from f of x. I'll just do this parenthetically over here. F of x equals 1 over x to the p. Remember, we just marry our sequences. Sequences give us the values. We marry our sequences to the function. So whatever is true about x, 1 over x to the p over here is true about the series, 1 over n to the p. So cool. So given this, I know that this thing, 1, will converge if p is greater than 0. Ripley. If p is greater than 1. And it will diverge if p is less than or equal to 1. Now you may say, wait, why is it if it's equal? Well, if p equals 1, we got the harmonic. We already showed that that thing diverged. So cool. Look at this. So now we have an integral test. We have a p series, which is absolutely fantastic. Now think back to improper integrals. I know many of you suffered through improper integrals, but think back to them. Do you remember what else we got?